Okay, so first, a coordinate system. Well, I guess let's read our stuff. Thank you, Jennifer. This is page 139 in the textbook. And we're going to kind of jump through this a bunch. So our author is pointing out that we've used this word graph to refer to bar graphs and pie charts. And they are the representation of data. It's like a visual look at it. But that's a kind of real general use of the word graph. It kind of fits. What we're going to talk about now is what you do in algebra, and that is the XY coordinate plane, which is what we mean by a rectangular coordinate plane. And what we do with this is we're plotting points that come in this form. X comes first, Y comes second. That's the order. Why? Someone chose it. We could flip them if we wanted to. It doesn't make a difference. We've just kind of standardized things so that we all kind of are talking about the same thing when we do stuff. The higher level math you go, we do all kinds of stuff with these axes, label them all kinds of different things. So the first thing we're looking at here is here's a data set, and it's data over time. And notice this data set represents the percentage of adults who are willing and able to work but don't have jobs. It's called the unemployment rate. And we've got it, this is actually the average unemployment rate for these particular years. I don't know if you all pay attention to the news and how this happens. There's always the monthly jobs report comes out, and then everyone blames whoever's in charge of the government for whether that's a good number or a bad number, and people are watching it all the time to see, is unemployment going up, is it going down? And it's one indicator of how well the economy is doing. There are other things like inflation, you know, the cost of gas or food and all the rest. I've seen political ads recently in Michigan talking about how the high grocery prices is the fault of our governor, and the high gas prices, or at least that's what the ad is suggesting. May or may not be true. It's maybe an effective tool to suggest don't vote for this person, right? So this is the kind of thing that you're going to encounter in the world, these kinds of numbers. And here we're just looking at a pattern. Do you all see the pattern when you read these numbers? Can you describe it? The trend? Oh, and before you do, you should note that this table is really bad because this part is a continuation from here, right? Because here's 03, and then it should go 04 and 05. And so it really is all one table. We just broke it apart to fit it on the page. 26-year period. I bet some of you aren't even 26 years old. So tell me what these numbers look like to you. What's the trend? What's happening? Based on just reading the table. No clue? Nice. Okay. Yeah, I'm with you. Decreases and increases, then decreases again. All right. So what are we looking at? Let's see. Thank you, Jennifer, for that. We're looking at these numbers. It starts at 6.9. Oh, look, it's going down to 4.2, 4.0. Oh, it jumped. It's going up, up. Oh, went back down, down, down. Oh, back up. Oh, got crazy high. Anyone remember what happened in 2009? Does Bear Stearns ring a bell to anyone? So it jumped way up to 9% unemployment, and then it seems to be dropping again. I don't know if you were alive. People thought the world was ending back in that 08, 09. The stock market crashed big time. The housing market blew up. There was this huge bubble that just burst, and lots of people lost lots of money, except for the ultra rich. They just got more wealthy. And there were CEOs that got let go from their companies because the companies crashed, and then they got tons of money, and all the low level workers lost all their retirement. Bear Stearns. Okay. Hey, what if you looked at this? This is the same data set. Now, what do you think about writing a description of what happened? And that's the point, that sometimes looking at the raw data set, it's kind of hard to see what's going on. A mathematician looks at that and sees the numbers, and this is what's in their head. They see the rise and fall. But our author is trying to make the point here that oftentimes graphs are super nice for visualizing data and understanding what's happening. Notice that what we did is we wrote two variables. The x-axis here happens to be years, and the y-axis is the percent unemployment. We often don't write years like this. We often write them as 1, 2, 7, 12, and so on and so forth. Okay, so let's talk then about some of the language that goes with a graph. We've got things called coordinates that I already mentioned. Those are the x-coordinate and the y-coordinate of a graph. And then we have a special point on the graph. It's called the origin. That's where the x and y axes meet, and that's when x is 0 and y is 0. Also note the x-axis is referred to the horizontal axis because it's like this, and the y-axis is a vertical axis. All we've really done is smash together two number lines and created a system like an ordered pair system. So then when we plot points, we look at the x-coordinate and the y-coordinate, and we put them on the graph. So for example, this x-axis has a scale of 1. So this is 1, and then the y-axis has a scale of 5, no, 2s, 2, 4, 6, 8, 10. So if I wanted to plot the point 1, 7, it would go right here, because we'd go 1 on the x, and we'd go up 7 on the y-axis, and there's that point. Now, for me, I'm not interested in you being able to draw a graph by hand, because we have a tool that graphs everything for us, and it makes it perfect, and we can zoom around and mess with it. So we already did this one. We already talked about that, sort of. So let's look at how do we plot these things in Desmos. So everyone get to Desmos. And I want to make sure you all can get this exact same graph. Now, there's two ways we can do it. One way in Desmos is to write exactly what you see. So parentheses 4, 0. Notice it showed up here. I'm going to label that point A. And then 0, -8. I'm going to label that point B. And then let's see, -3, -4. That is going to be labeled point C, and you seem to be getting the point, right? 2, 7. So what I want to see happen, or what I want you to do, is make sure everyone can do that. Right? When you have a graph, when you've got these in Desmos, tell me you've done it. And I'll give you 3 minutes until I start wondering if you're there. Set a timer for 3 minutes. I thought I muted myself. Okay, Jennifer, it might just be me and you rolling on this. The rest of you, well, am I rushing you all? I don't want to rush anyone. I also don't want to waste anyone's time. Totally fine if you're just got this turned on and aren't able to do as much. Okay, Alyssa, you're done. Awesome. Awesome. Can I force myself to wait a few more seconds? Probably not. I've had too much coffee. All right. I want to do another thing. There we go. We got 3. Okay, good, good. Thank you all for that feedback. Turn off the timer. So there's a second way to put things in, and this is the far more important way. So I'm going to delete all these. You don't have to. I'm just going to delete them so they're not there. I'm going to click the plus sign in that top left corner, and I'm going to click table. Notice it says X1, Y1. So this is another way to represent ordered pairs. It's the same thing that we have here for this table, right? It's the year was the X, the rate as a percentage was the Y. So we've got this, Desmos has the same option, and I'm going to plot these 4 points in here. So I just do 4, oops, I gotta click in that, 4, 0, and then 0, -8, and then -3, -4, and then 2, 7. So same exact thing. One of the disadvantages of this is I can't label the points. However, one of the advantages is in the bottom left corner, there's this thing that says zoom fit. So I click that and we'll all have the exact same picture. And if I like really care about things, I can click this wheel and I can change the color, and I can change this stuff, and I can make them larger. I think what did that do? And I can make them, yeah, there we go. I can make them super large. I can connect them, which doesn't make any sense. I can make it so I can drag these points. None of that is actually important, but that's cool stuff you can do with this graph. My 2-year-old's favorite color is purple, so we're going to make it purple. And I'm going to put down the density to like 5. Okay. So this is one of the, ooh, that's really hard to see those little dots. What was it originally? This is one of those super important things that you need to know how to do. Maybe that's what it was. Because this is what you're going to be doing in your project and throughout the rest of this unit, is being able to put data in a table and then get a nice picture of it. Do you all need some time to do this, or shall we move on? We're gonna do it again. So let's move. Let's actually go to a bigger data set that I want you to put in there. So skip to this page, number 5. I'm going to write the first ordered pair. You don't really need to write these ordered pairs in here unless it's something that you are struggling with. So couple notes of what we've done here. It's often that we don't like to use the year as an X value because it's super large. Like it's way down the X-axis. Like if we go back to Desmos, or where are you, Desmos? And I put in the point 2006 and 2.32, like it's crazy off the chart. I mean, it's like way over here. And so we often don't like that. We want things closer to the y-axis. So instead of putting in years, we reinterpret them as years after some starting year. And it's always told, we always write it. So here we're going to do the number of years that have passed since 2006. Well, if it's currently 2006, that would be considered year 0. And then 2007, that's 1 year after. So that would be a 1. So what I want you to do is fill in a new table with these ordered pairs. These as ordered pairs. You don't have to write all these, you just need to type them in the table. All right, so the first one, the X1 is the number of years after 2006, and the Y1 is the January price per gallon. So I'll give you like 3 minutes to do that. Set a timer for 3 minutes. Awesome. Okay, now I got to catch up. Now, did you all click the Zoom Fit button so you get a nice clear picture of what's happening with the average gas price for January over these years? Like if you left the picture from the last one, it's not a very good one, right? I mean, look at this mess. It looks like a vertical line. So it's not a helpful graph, but if we click the Zoom Fit, we see this little pattern going on. Awesome, you all. Now we can, we could connect the dots here. Let's see. Wait, what are we doing? We want to do this. We want to do this. And you could do that. Oh, hello, friend. You can stop. You can do that. And really, we shouldn't. We're not going to be doing this. This kind of shows like a trend. It's creating lines between each of the data values. What we're going to do is find a line that's best for all of them, that goes through all of them. So generally speaking, don't do this. But sometimes it's nice to help visualize kind of, oh no, what's going on. So see how I accidentally deleted my table? This button allows me to undo what I just did and get it back, so I don't have to retype everything. Super nice. You can also just do Control Z. Okay, so with our graph, our author, oh, wrong button. Our author says, plot these things, and then we're supposed to draw it here, and we're supposed to label the axes. So let's, hey, Jackson College, let's do that. In Desmos, we can label our axes under the graph settings. There's a bunch of different stuff here you can work on, mess with, but here's the x-axis, and we want to label this as years after 2006, and the y-axis is the average January gas price. And so now we have that verbal description of the two axes that helps us keep track of exactly what's going on here. I feel like zooming in might be nice. You can also zoom around with things. I'm using the scroll button on my mouse, that thing, to zoom in and out. You can also, do plus signs, but that's a set amount of zoom. There you go. Okay, so can we describe a general, actually, no, let's do this. Oh, yes, let me do that again. I went to graph settings, and in here, there's this x-axis. It's clicked so that it's shown, and then you can type right in here what you want to label the axes. And same thing with the y-axis. You can also click display to make everything bigger. So if you're going to copy this graph, say into a project that you're going to be doing for this chapter or so, that might be a nice way to help us all see a little better what's going on. Note, you can also click all of these ordered pairs and it puts in the values from the table if we wanted to do it. So I'm just clicking them. If you click the screen again, not on top of one of them, they disappear. So just things to keep track of. Okay, so that's a lot of stuff. There's a few other little things in this section I want to note. He's got a great question here. What temperature is this thermometer displaying? And we're all like, what? You look right here and it's something, one of these numbers, but it's garbage because there's no scale. So like in project 1, if you turned in a bar graph or a pie graph without any numbers on it, it's kind of not very good. Those aren't as terrible. This one where the numbers are, reading this is really important. Scale is absolutely necessary because that scale could be anything. We have no idea what it is. It might be a standard thermometer, it might not be. So whenever you turn in a graph, make sure it has a sense of scale on it. And that's what's nice about Desmos is it always has scale in there. It's just defaulted. Let's do one more scatter plot. No, let's go on to the next section. Let's just be done with 2.2 because that's all we need. We just need to know how to graph things. And what's going on here? Okay, and let's go to 2.3, and here's where we're going to use these new graphing skills to help us. So this is a page after 139, quite a ways after 139. And what we're going to do here is we're going to learn about what a rate of change is. Thank you. Oh, Caitlin, great question. Let's do the 2.2 lesson check. That's such a good idea. Since we've made our way through here. So let's get logged in there. There isn't a 2.2 worksheet, really. There's 2.3 worksheets because they got mislabeled when I made them. So we'll talk about those worksheets in a second. Once we get through 2.3, we'll look at the worksheets. So the 2.2 lesson check, it is what are the coordinates of the origin? 0, 0. Those are the coordinates of the origin inside parentheses. Let's see if this accepts that as the answer. It does. Good. So you have to have the ordered pair part, parentheses, and then the 0, 0. It's the spot where the axes intersect. So that point is a really special point. It's both a X-intercept and a Y-intercept all at once. Okay, now let's do 2, 3. Yeah, looks like my buddy is playing The Witcher 3. Great game. Okay, so we're going to look at rates of change. Now we already know rates of change because we did that back in section 1.4, and there were 2 things that we learned with rate of change. One of them we just learned, hey, there's the word rate, and it's A units divided by B units, right? And it's just a whatever. And then the second thing we connected with that is the notion of a unit rate, and that's A units divided by 1 unit. So often we did A divided by B. Like if we had a rate and we wanted to convert it into a unit rate, we divided A by B and then kept a 1 in the bottom with as that many units from B. So keep that in mind. That's still super important for what's happening here. We're going to note that we can use a rate of change to predict future values if that rate of change is constant over time. Wait, what did we learn about lines? How do we tell if a relationship is linear growth? Back from 2.1.
It's adding by the same constant.
Nailed it. So this is saying if we have a rate of change that's constant, then we're talking about a linear relationship, and we can predict those future values. So we're going to learn how to calculate that rate of change. We're going to see how that connects to the line. Surprise, it's called the slope. And then we're going to look at this idea of a Y-intercept and an X-intercept, and we're going to figure out how to interpret them. So let's start here. We're going to skip all these different rates of change. And we're going to start with another definition of rate, or it's a repeat of that. A rate is a ratio that compares 2 quantities. Often we see the word per in that relationship, and per means divide by. And so we can write the verbal description as a fraction. The key thing is to keep the units in there. Now, I know we often write this one as MPHs, but that I think can be misleading because it doesn't remind people that we're dividing that 88 by 1 hour. It's a unit rate. Okay, so equivalent here, we already know this from before, right? We talked about equivalency statements that we could then write. We could use those statements to write conversion factors to do dimensional analysis, meaning to convert between different units. So if things are equivalent, they mean they're equal to the same thing. That's what we're saying. So for number 1, if you make $100 a day for doing a certain job, how much money would you make in a 5-day work week? Interesting. So if we did this unit wise, the rate we're getting is $100 per 1 day, right? That's the rate that this is talking about. And then nailed it, Jennifer. If we did this for 5 days, now notice me doing this dimensionally. We're going to multiply this rate by this 5 days. The days cancel, and we're left with just dollars. $500. That's maybe more complicated than you needed to do, but I think thinking this way, writing things out this way and thinking this way can help you get through the more complicated problems, even though you probably could have done this without writing anything down. So then our author says, well, wait a minute, are these the same thing? $100, oh, if I could write $100 per day per 1 day, is that equal to $500 per 5 days? And everyone's like, yeah, look, if I convert this to a unit rate, so this one's a rate, this one's a unit rate. If I take the 500 and divide it by 5, I get 100 over 1 day. So yes, they are equivalent rates, meaning they're the exact same thing. Boy, someone should teach me how to spell exactly. My goodness. All right. What this tells us then is that we can mess with our rates. We can change them as long as whatever we multiply by is 1. In other words, as long as we multiply the top and bottom by the same thing. So this is kind of a cool one. What if we take 60 miles per hour and we want to turn it into however many miles we can do in 2 hours? So we want to change it so that it has a 2 down here. Well, if we divide the top and bottom by the same number, we get 30 miles per 2 hours. Well, and then the author's like, well, wait a minute. What if we want a 1 in the denominator, meaning convert this to a unit rate? Well, then all we have to do is take 60 and divide it by the 4. And how do you feel? Does that feel like 15 miles per 1 hour? It was easier for me to take this fraction, 30 divided by 2, and do that simplification than 60 divided by 4, but whatever, it's all the same. So there's our unit rate. Note that 60 miles per 4 hours, 30 miles per 2 hours, and 15 miles per 1 hour are all the exact same rate. They're all equivalent statements. I think we could all argue that the very last one is the one that makes most sense to us, like has the most practical meaning. Because this tells us, oh, you're not going very fast, whatever you're doing, unless you're running. If you're running, that's pretty good. If you're driving a car, well, come on, get off the highway. So number 5, here we want an equivalent fraction to $320 made in 4 days. But what we want to do is scale it up to get a denominator of 10. In other words, how much money would we make in 10 days? He suggests first scale down, meaning, I don't know, divide the top and bottom by 4. So then we get that this is $80 per 1 day. That seems pretty close to sub pay in like the high schools and elementary schools. Might be a little higher. And then if we want to scale that up, we could multiply the top and bottom by 10. And we get that an equivalent rate or equivalent fraction to $320 per 4 days is $800 per 10 days. To me, a more useful one would be 7 days, because that's your work week, right? No, 5 days. 5 days is a work week. How we doing? Okay. I know everyone hates fractions, but I think if you think of these as not fractions, as units over units, and keep track of those units, maybe it's not too bad. I don't know. Okay, so I'm going to let you all try this one. So we got someone bicycling or pedaling at a rate. Yeah, I'm with you, Mike. Like, why would part of it's like the reason you want you to scale down is if we want to go from 4 to 10, we have to multiply by 2.5, which isn't a big deal, but maybe it is, because this isn't a nice whole number. I don't know. I'm with you. Okay, so if one bicyclist is pedaling at a rate of 40 miles in 3 hours and another is doing 50 miles in 4 hours, which is faster? So let me give you 3 minutes. Figure it out. Who's faster? Set a timer for 3 minutes. Okay, who's faster? Turn off the timer. How did you know the 40/3 was faster? What did you do to solve that problem? So how'd you all know that? You're right, by the way, I totally agree with you, but what did you do to get that? Did you say that 40 is less than 50 and 3 is less than 4? Yeah, right, you did. So what you did is you converted it to a unit rate. That's one way to compare it. 40 divided by 3 is 13.333 miles per hour. We'll just say 13.3 repeating miles per 1 hour. Nice. Yeah, nice. And okay, and then this one is that's a weird squiggly line, 12.5 miles per 1 hour. So because this number is larger than that one, that's faster. Perfect. I saw in my in-person class when some people were solving this problem, they multiplied by 4. So they got that this is 160 miles per 12 hours. And this was 200 miles, not 4. Oh, and then I'm sorry, and then they multiplied this one by 3. So they did this 4/4 and this one 3/3. So they got 150 miles in 12 hours. And so this person got further. They got 10 miles further than the other person. Thus, they're faster. Doesn't particularly matter which way you solved it. Any way is acceptable as long as you know that you're right. Awesome. Okay, so now we're going to look at, well, what happens if we keep this pace? What happens if we stay constant? So our author says most experienced runners get to a point where they can comfortably, experienced runners don't use the word jog. Runners talk about running, or they can comfortably run long distance at a consistent pace. I believe it's called splits. And if any of you are track and field people, let me know the correct language. So this pace, of course, is another way to say rate of change, meaning they're running at the same speed for hours and hours on end. It's how you conserve your energy or whatever. So here we go. We've got one runner. I don't like the word jogs. Runs 1 lap around a 400-meter track in 2 minutes. If they can maintain this pace for a long time, awesome. We'll get that for every 2 minutes, the runner runs 400 meters. So let's fill in the table, and we're going to go with steps of 2 minutes. So 2, 4, 6, 8, 10, 12. Note what we're doing. Every 2-minute time step, we add 400 meters. So this would be 800. This would be 1200. Then we're hitting the 1600, then 2000, and then 2400. So there's our table. Let's graph that real quick and just see what does that look like graphically. I'm going to delete this old table. Nope, I don't need a note. I do need a table. And we're doing 2, 4, 6, 8, 10, 12. And then we're putting in the 400, 800, 1200. Oh, I did 12,000. Easy killer. 2,000, 2,400. And then I'm going to do my zoom fit. Look at that. Although I've got these labels that I don't want on here anymore. So this is distance. And this is time. And I guess we should say in minutes and in meters. So we understand what the units are. Okay, so there's our graph. Note that looks super linear, right? It looks like all of the values are on the line. All of these points are on a single line. Okay, so notice that the rate at which the runner's distance changes is constant. When the rate of change is constant, a quantity illustrates what type of growth? What? When the rate of change is constant, a quantity That's a typo. It's got to be a typo. When the rate of change is constant, I can't figure it out. Yes, excellent. It's linear. We're adding the same amount each time step. So we're adding 400 meters each time step. Good, good. Okay, so we're going to do this as a fraction. Notice it says write the runner's rate as a fraction using meters in the numerator. In other words, what we want is meters per minute. That's typically the language you're going to run into. So it's 400 meters per 2 minutes. Now look at these units, the unit abbreviations. They're super similar. So be careful. Meters, minutes, and miles are all start with the same letter. Here's meters, here's miles, here's minutes. If you think you're going to confuse those two things or those three things, write out the full words to keep track of what's what. Okay, so we're supposed to write this as a unit rate. Well, that means take 400 and divide it by 2. So really, another way to think about this is the runner is running at a rate of 200 meters per 1 minute. This is the best measurement, the metric system. Author says, oh, let's go to meters per second. That's, so we're going to use some dimensional analysis here back from Unit 1. And we want to convert these minutes into seconds. So first we need to remind ourselves that 1 minute is equal to 60 seconds. That's an equivalency statement, right? We can write that as a fraction or as a conversion factor. So question, what conversion factor should we use? Where should the minutes go in my fraction? Top or bottom?
Top.
Nailed it. Why the top?
So they can like cancel each other out.
Nailed it. And then we get what we're wanting here. We want minutes divided by seconds. Excellent, y'all. You're crushing it. So let's see. I don't know what 200 divided by 60 is. It's 20 over 6, which is 3.33333333 forever. So this is approximately equal to 3.33 meters per 1 second. I don't know if that's super fast or not. I don't know. I used to run, but I didn't really track my data too much. Okay, so now we're asked to use these rates to do some calculations. So we're saying, hey, if this person runs for 40 minutes, how far are they going to get? Well, we have 2 rates to pick from, right? We have rate A and rate B. Notice that this one is in meters per minute. This one is in meters per second. If I'm using 40 minutes, I'm going to want to use the meters per minute rate to do this calculation. So I can multiply this using dimensional analysis. And I can see that the minutes cancel and we're just left with a total of meters. So what? How do you feel about 8,000 meters as the distance? And then 14 is like, well, how about if we were doing 40 seconds? Well, same thing. We could pick either rate we wanted to. Why not use the one we already found, 33.33 meters per 1 second? And if we multiply that times our 40 seconds, the seconds will disappear and we'll be left with however far that is. So I'm just going to take this number multiplied by 40 and we get approximately 133.33 meters. How are we doing? Oh, I still have a little bit of coffee, so we're doing good. It's mostly grounds at this point, and it's cold, but you know, who doesn't like coffee? Awesome, Jennifer, awesome. All right. This asks you to think about physics. So based on these previous two questions, we can write a formula for finding the distance. Note, nice, Mike. Note this is time, and this is speed, and this is distance. So this is the distance formula you may have encountered in a high school physics class, or often we toss it into a like an algebra class. Distance equals rate times time, or speed. There's another word for rate. So that would be D equals RT. We could also solve this for the other pieces. If we want to know how much time did it take us to travel a particular distance at a particular rate, we take the distance and divide it by the rate, and we get the time. Or if we know how far we went and how long it took us, we can get the rate or speed by taking the distance and dividing it by the time. Those are like three common formulas. They're all related by the same thing. So if I did it symbolically or with letters, we'd say time equals distance divided by rate, and rate equals distance divided by fail. Double fail. Distance equals rate, or rate equals distance divided by time. We can use dimensional analysis to show why all of those things work if we wanted to. Okay, so if we skip down to question 16, we can now use our rates to do a little bit of a calculation. So what would this runner's total time be for a 10K race? If they kept that pace, they use that rate of change. Remember, we had it as 200 meters per 1 minute. We want to know how much time will it take for them to run a 10K race. Now, we do have a problem here, right? This is in meters, not kilometers. So let's convert this rate into kilometers per minute. So the way to do that is to take our equivalency statement here and turn it into a nice fraction that removes the meters and leaves us with kilometers. So that means we want the kilometers on top. We want the 1,000 meters on bottom. Swoop, swoop. Boy, well, it's kind of a gross number, isn't it? Let's see. These two zeros go away. It's 1/5, or let's see, 200 divided by 1,000 equals 0.2. So we're traveling at a rate of 0.2 kilometers per 1 minute. Ooh, should have added the minutes there. Easy. Okay, so now what we can do is take our 10K race, and I'm going to do this using dimensional analysis. I'm going to multiply this by the rate, but I'm going to flip the rate, because in the end, what I want to be left with is just minutes. So I'm going to multiply this 10K by 1 minute divided by 0.2 kilometers, or 0.2 kilometers. That way, these kilometers cancel, and we're left with time. Let's see, 10 divided by 0.2, what is that, 50 minutes, is that right? 10 divided by 0.2 is 50. I don't know, that seems like a little bit of a slow 10K. That might not be a competitive rate. I could be wrong, though. Have I blown anyone away? Are we doing okay with this? I guess we'll find out in a second if it made sense or not. Okay, so that's rates. So let's pause. Oh, go ahead.
I'll put your computer back in 2 seconds. Freddie, I need you to finish up. You got...
Laquita, I muted you. If you wanted to ask a question, go for it. But you sound busy. What I want to have you all try is this problem, messing with rates. It's a tough one, so get ready. It's so in your course pack, it's the second 2.3 worksheet. Oh, do I have answers on it? I hope I didn't save the answers on it. It would be easy. Yeah, no, it's the first one. Oh, it says 2. So mine says 2.2. It's actually 2.3. So it's page 22. So on page 22, try this thing. By the way, this guy used to hold the record for the Berlin marathon, 2 hours, 2 minutes, 57 seconds. It was just beat like yesterday or 2 days ago by a new person. So I'm going to give you 5 minutes to try this. Is that enough time? Yeah, let's do 5 minutes and see if you can't get A and B. Set a timer for 5 minutes. Okay, that was 5 minutes. Anyone got an answer for 1A? Or anyone totally lost, or anyone just need more time?
I accidentally converted to seconds.
Nice. That's okay. And then you could convert all of those seconds back to hours if you wanted to. Because you need, although, let's see, do you need, oh yeah, you don't need per seconds. One of the things you all might need is that 1 minute equals 60 seconds and 1 hour equals 3,600 seconds. And if I had someone in my in-person class say, can't we just call this 2 hours? And I'm like, no. Like a sub 2 hour marathon or someone running a marathon in 2 hours is insane. No one has done it ever. Actually, one guy did it, the guy that just broke the record recently, but he did it in what's called laboratory environment, meaning I think he was running on a treadmill where they controlled the temperature and everything. Because that has, you know, temperature and wind speed and everything has an effect on how fast you can run. So you've got it. You can't throw away those 2 minutes and 57 seconds because that's a huge deal. In fact, the guy that broke the record the other day broke it by 30 seconds, which is just insane. The man's a beast. Marathon beast, we should say. How many hours is 2 minutes? Anyone got that number? What are you doing? And how many hours is 57 seconds? Anyone got that number? This is how I might organize it. Okay, yay. So the first question isn't a rate thing at all. It just says, let's turn Dennis's time into total number of hours. So to figure out how many hours 2 minutes represent, by the way, it's less than an hour, right? We need to use this equivalency statement to write a conversion factor that converts this into the amount of hours 2 minutes represents. So because I want the minutes to cancel, I need, oh, but I got this wrong because that's the wrong, no wonder you're lost. This is useless. 1 minute being 60 seconds doesn't get us anywhere close to hours. We need 1 hour equals 60 minutes. So I'm going to put the hour on top here, and I'm going to put the 60 minutes on the bottom. And that's going to cancel these, and we'll figure out how many hours 2 minutes represents. It's 2/60ths of an hour, or 1/30th of an hour. Likewise, over on the seconds, I'm going to do this 57 seconds times 1 hour divided by 3,600 seconds. And we're going to get that 57 seconds is 57 3,600 seconds, 3,600 seconds. No, I don't even know how to say that. So this feels like a great Desmos sort of situation. I'm going to get here 57 divided by 3,600. There's those seconds. And I'm going to take 2 and divide it by 60. And there's the minutes into hours. So we're going to have to round this. I'm going to do 0.01583 for the seconds. So 0.01583, that's approximately how many hours 57 seconds represents. And the other one, oops, wrong one. The other one is, wait for it, where is it? Here it is, 0.033. 3333 is 2 minutes is that many hours. So I will do, let's do 0.0333. I'll do three threes. Maybe I should do another one to match how many decimals I rounded this to. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So that means if I add these three amounts together, since they're all hours, I will get the total number of hours Dennis Komodo was running. How does that feel? 2.4916 hours.
I mean, do we really have to do it this way though?
How would you have done it?
I just converted it all into seconds and then divided by 60 twice.
It's awesome. That works too. You don't have to do that. Yeah.
Okay,
So what? You had 7,200 seconds
well,
plus
73, 77 divided by 60 and then divided by 60.
yeah, there you go. 77.57 seconds, and then divide that by 3,600. Let's see, do we get the same number? Drum roll, please. Of course we do. It's the same thing. 7757 divided by 3,600. What? Why is it? Wait.
You
Oh, it's
added,
because it's same.
should be,
Nice typer.
yeah, 7.3.
That's because I can't count. Okay. 7357 divided by 3,600. There we go. 2.0436111. I have 2 point. Seriously, what did I?
It should be 7377 divided by that, I believe.
Curse words. Yep. Third try is a charm. Swoop. 2.0491666666666 forever. Yes. So technically, if you rounded to 5 decimals, it should be 17. Because I rounded earlier, so this answer is more accurate. Because I rounded these numbers, my 6 stays a 6. Doesn't particularly matter. We've got hours. Awesome. Now, do you all know how to then use that to calculate his average speed? Note miles per hour. So how far did this guy run?
Would we then just divide by 26.2?
You might be thinking the right thing, but said it the wrong way. You're going to take 26.2 miles and divide by 2.4916, which might have been what was in your head. And how do I know that, by the way? How do I know the miles needs to go on top? It's because of the order here. Oh, sorry. Go ahead, y'all.
For your answer up there, isn't it supposed to be 2.04916? Not
Mhm.
2.4.
Boy, it's just one of those days. Yes, thank you. This is why we have proofreaders. Does everyone feel better now? Yep. See, there it is right there. Should be copying and pasting. Okay. Are we happy with this number? I think this isn't correct because of the English. Do y'all get what I'm saying? It says miles per hour, not hours, which implies a unit rate, which implies we want a 1 in the denominator. So let's do that division. 26.2 divided by 2.04916. Look at how fast this guy was going. Does this blow your minds? He was running at a rate of 12.79 miles per 1 hour. And he did that for 2 hours, 2 minutes and 57 seconds. He did that straight. That was his pace. Now, there might have been some points where he ran a little bit faster, like right at the end when you can smell the end zone or whatever, or maybe he just paced himself and that was the speed he went the whole time. But that's crazy. How are we feeling?
Fairly good. I still have trouble with the conversion factor part of it, but other than that, I'm with you.
Well, Mike, you said you went to seconds first, right?
Yeah.
So was that
Thinking
better?
that was the yeah, it was. I was thinking
Do
that was
that.
the problem, and I did like it was like 7,000 something seconds.
Good, good. Yeah, if this made more sense to you, forget all this mess. Do that one. You don't have to do the dimensional analysis the same way I'm doing it. It's the one that makes sense in my head because it's how I've been doing it for a while, but that don't feel like you have to do, if you had a strategy that got you there, like converting to seconds and then dividing by the total seconds in an hour, that's awesome.
Well, I still didn't get to the right answer because I didn't convert the seconds to hours. I thought that the problem was to figure out seconds.
Got you. That's okay. Right. That's a cool one. That's not the one I asked for, but it is an interesting one. How many miles per second was he going? Oh, I guess that one doesn't make a whole lot of sense, does it? 0.04 miles per second. 0.004. Cool. A little more practice will help, I think. I'm going to go back to the notes so we finish it. Just note this. I want the next one you calculate to be minutes per mile. So you can take this one, but you have to flip it and then convert it into minutes. And then when I say interpret your answer to B, what is that? This should say from C. Interpret your answer to C in the context of the situation. Here, I just want to know, what does this number mean that you calculated? So just write a sentence that says what it is. There's not like a when, what, and how much kind of thing for that. And then this here, there's just 2 more unit rate things to write out. I'm going to let you all try that, and then if you get stuck, come ask me. Like, we can do it in class on Monday, or you can come to office hours or whatever. What I want to do is go back and finish this section because there's a little more we got to get to. Okay, so we're back on this page, whatever page this is. Back in 2.3. and we're going to work with a graph. Now, anytime you see a handwritten, a graph where you're supposed to draw it by hand, don't do it. Use Desmos. This graph, the scale, like these aren't square. They're awful. So this is a really bad graph to hand draw on anyways. All right. So our author looked up taxifarefinder.com, and if you're going from the airport in Las Vegas to anywhere, you get charged $5 initially, plus $2.60 per mile. Notice that language there, $2.60 per 1 mile. That's a rate. This is a flat amount, a flat fee. So we're going to fill in this table. That means for each mile we add 260. So here 510 plus 260, 770. 770 plus 260, 1030. Add 260 to 1030 and we get 1290. Add 260 to that and we get 1550. Add 260 to that and we get 1810. So then we're supposed to graph it. Okay, fine, we'll graph it, but we're going to do it in Desmos. We're not going to do it by hand. There's a couple ways to get a new graph. You can just do this new blank graph by doing plus. It deletes everything else. If you wanted to save your other stuff, you do whatever you want. I'm just going to do a new blank graph. I'm going to enter my table and 0, 1, 2, 3, 4, 5, and then my numbers. And then my zoom fit. And here's my nice picture of my graph. I might even put in here that the x-axis was distance and the y-axis was cost. And this was in miles and this was dollars. What does that graph look like to you? The author says, what do you notice about the pattern that the points on your scatter diagram are making? Use this.
Looks like it's linear.
Yeah, nailed it. It looks linear. Surprise. But we know that, right? Because we were adding a fixed amount. We were adding a constant each unit step. So it looks linear. He says, draw a line. Okay, we can do that here. We just do our this thing and turn on the line. And yeah, they're all those points are on the exact same line. This is appropriate to do. Excellent. Okay, so it looks linear. How do we know that? We're adding a constant. And that constant is the rate of change, which is 260. That's important. That happens all the time. It's called the slope. Surprise. So here we get a definition. The point where any graph crosses the y-axis is called the y-intercept. And where it crosses the x-axis is called the x-intercept. So if we were to write those as ordered pairs, the y-intercept always occurs at 0, some number. Let's call it b. And the x-intercept always occurs at, let's call it a, some number. That's what they look like. So if we look at our graph, you can see where the y-intercept is. It's right here. 0, 5.1. So for us, it's 0, 5.1. If you think about the units on that, this is miles, this is dollars. So one way to write that out practically is to say the cost to climb into a cab is $5.10. $5.10 to get into the cab. An X-intercept. So if we look at our graph, there isn't one. But if we were to continue this pattern, it would be somewhere back here. Well, what's a negative X value represent? Nothing that makes sense, right? So the X-intercept doesn't make sense. I guess we just say it doesn't make sense because it would be negative distance. What, did the cab driver go in reverse? And so he's going to give you money? Negative distance, whatever. All right. So now our author says, how much more will you pay for a 3-mile ride than a 2-mile ride? Well, if we look at our table, the cost of a 3-mile ride was $12.90. A 2-mile ride was $10.30. Wait a minute. When we do that subtraction, we get $2.60. Didn't we already know that? Each mile we add adds another $2.60. Okay, well, what about if we did a 5-mile ride versus a 2-mile ride? Okay, so the 5-mile ride is $18.10. The 2-mile ride is $10.30. So I don't know, what is that? $18.10 minus $10.30 is, $7.80. If you think about what happened here, the rate was $2.60 per mile. This is a distance of 3 miles. Let's see, what's 3 times $2.60? Oh, I know, it's $7.80, right? So because it's a fixed rate, we can use that $2.60 to do all kinds of calculations. Well, now the author says, pick any 2 points, subtract the second coordinates, then divide the result by the difference of the first coordinates. That's wonky. What he's saying, the second coordinates are the Y's. The first coordinates are the X's. So I could pick the point 5, 18, 10, and the point 1, 770. And what he wants us to do is take the 1810, subtract the 770, and then divide that by 5 minus 1. That's what he's pushing us towards. Let's see, 1810 minus 770. Oops, 1810 minus, that's plus, come on. Minus 770 is 1040. What do you suppose 1040 divided by 4 is? Dum, dum, dum. Oops. It's 260. What? Yeah, so that's the rate of change. In other words, what he was trying to trick us into was the slope formula. And that is, if you want to calculate the slope or the rate of change of a line, you subtract the y coordinates and then you subtract their x coordinates, keeping the order of the first y coordinate you chose has to be the one that comes first for the x. You've probably seen this formula before. I don't see this as super useful. I think what to me is most interesting is to think about this formula is really talking about how much up and down change, how much y change has happened. By the way, this little triangle is the Greek letter delta, and it stands for change. Think of change as new minus old from unit 1, same idea. So visually, what happens here is we can take a line, we can identify 2 points on it, and we can form a triangle that represents that change. So I already calculated these values. The x-axis change, the distance from here to here, represents the difference between the 5 and 4. So the 5 and 1, that's the 4. And the horizontal change is the distance between the 1810 and the 770. That was our, what was our number? 1040. And so what we can do is say, well, here's the rate of change between these 2 points. That rate of change is 1040 divided by 4. And if we think about the units on these, this was dollars. and this was miles. If we want that to be a unit rate, we just simply divide 1040 by 4 and we get the 260 divided by 1 mile that we already knew about. So this is what we're trying to get you to see here is when we have that constant rate of change, when we're adding the same amount each time, what we are finding is the slope of the line. And we can find it numerically doing these calculations. We can find it kind of graphically by looking at this sort of relationship between the 2 points. It doesn't particularly matter. Oh, I did all these questions at once. How are we doing? I've had lots of coffee, which makes me kind of go fast. You all feeling okay? If we were to answer his questions here, it should look like this. Okay, all right, good, good. So he does some fun things here. I don't know. He says, how much would 4 miles add to the cost of a taxi ride? Well, if it's 260 every mile, we're just going to say 4 times 260. That's the new cost. What is that? 28. Oh, that's 1040. Oh, that's what we already did, right? We already calculated that. And then it says, would it matter if it went from 1 mile to 5 miles or 20 miles to 24 miles? No, because it's constant. It doesn't matter if we've gone 1,000,000 miles. We're always adding 260 for each mile, at least under the particular scenario. In reality, I don't think a cab driver would drive you that far. Okay, so the thing that makes a line is the fact the slope never changes, right? That is the constant. So we know that the slope of a line describes the rate at which the y coordinate changes compared to the rate at which the x coordinate changes. So if we wanted to decide if our 2 quantities are linear, we're looking to see if that's constant over all the points. The slope should be constant between any 2 points, actually between all points. All right, so whether we do the first and the last or the middle 2 or any combination, they should all be the same. Okay, so now the author does some fun stuff. What if we want to guess how far we could go for a $16 cab ride? Well, let's go to our data set. Come on now. Come on. Shoot. And 16 comes between 4 and 5, right? 16 is closer to this 550 than this 1810. So I'm going to guess it's like 4.2 miles. And my reasoning there, right, is what I talked about is 16 is closer to 1550 than it is to 1810. I looked at the table. We could look at the graph. If I graphed y equals 16, oops, I could find it exactly. It would be, I'm gonna zoom in a little bit. Looks like I was really close, 4.19. According to that. Although it's hard to tell if I'm exactly on that green line. Let me zoom in a little more. Here we go. Yeah, I'm pretty good. Okay, so that was my guess. We could find it exactly by writing the equation, but apparently we're doing that later. This really seems to have jumped. It looks like they're missing stuff. Okay, whatever. All right, so now we're going to switch gears. We're going to look at a new question. Here we're looking at a car. We know it decreases in value over time as it gets older. So we're going to say we bought a car for $15,000 and we know that it decreases at a rate of 2,000 per year. Notice decreasing would be a negative number and it would be negative 2,000 per 1 year. So our author gives us the table of values and the graph that's associated with that. And we're to find the y-intercept. Well, that's just the initial value. That's the starting value, right? And we're supposed to explain what it means. Well, that just means at time 0, so at year 0, the car cost $15,000. Or maybe we should say it was worth $15,000. Another way you could say this is the initial price of the car or the initial value was $15,000. So when we talk about the y-intercept, if I'm asking you to find it, you have to write it like this. That is a y-intercept. It is a point, not a singular number. That's what our author is pointing out here. And you should keep track of the units on it for interpretation purposes, like if we're to explain what it means. You're going to be doing this in your project, in lots of worksheets, and on the midterm, you're going to have to identify what is the y-intercept and what does it mean. And it's just for 0x units, in this case time, in years, the y value was this. Now we're supposed to find the slope of the line. Well, what we're needing to find is how much change happens per year. Oh, we already know it, right? It's right here. We were told it. We could have calculated it by taking the 2 points and doing the slope formula. You may remember that from an algebra class. Whatever, we were just giving it to it. What is the significance of the sign? Oh, that's the decrease. It's losing value. Okay, so now we're supposed to estimate the value of the car after 42 months. Well, that's a problem, right? Because our time is in years, not months. So we need to figure out how many years are 42 months. Well, I know that 1 year is 12 months. So if I divide 42 by 12, I will get the number of years. It's 3.5 years. What do you want? So I don't need to estimate it. I know exactly what it will be. I just take the negative 2,000, multiply by 3.5, and I'm there. That's the exact answer. Oh, wait, no, this is how much it loses. So it's going to lose $7,000. We started with 15,000, so we know the value of the car, it's going to be worth $8,000 based on this criteria. If we're going to guess, what is it? When is it going to be worth 6,000? It's going to be between year 4 and 5, and it looks like it's exactly halfway between year 4 and 5. So I'm going to say in 4.5 years. We'll get there. Okay. How are we doing? What you're doing in the homework now for the second 2.3 worksheet is you're going to draw a graph. And one of the things is you're going to write out the correct X values based on what this says. Paste your Excel thing here. I'll show you how to do that right now. In Word, you do insert. And I would do screenshot and I would do screen clipping. Oops, well now, and there it is, but you have to have opened what you want to show. So you can do that. If you're not doing this, if you're if you're doing this digitally, go ahead and do that. If you're not, don't worry. I just want to make sure you can graph. So, and I will know later. So I don't worry about if you have a hard time getting the graph on here. And then the second thing is I want you to graph these values and see what kind of shape do you get. And then I want you to identify a slope and a y-intercept here in question 5. Don't worry about writing the equation yet because we haven't talked about that. We'll talk about that on Monday when we do 2-4. So how about I give you like 5 minutes? Well, actually, what do y'all want to do? Maybe you should just go work on this because we've covered everything I want to cover. And then ask questions. How about this? I'll stay here for 10 minutes if you want to check if you got it right. If you're like, hey, I'm sick of seeing your face, which is totally fine, then take off and we'll see you again on Monday. Yeah, I guess that's all I have to say there.